Hello, good afternoon or maybe good evening towards your time, everyone. And my name is Chandan Bose. I'm an assistant professor of aerospace engineering at the University of Birmingham. And this work is done in collaboration with my colleague, Dr. Yabin Liu, who presented in the morning. He's a Brunel Fellow at the University of Edinburgh. And also, I would like to acknowledge my master student, Nikitas, and my postdoc advisor, Professor Ignacio Maria Viola. So today, basically, I will be giving you a brief overview of the overset meshing strategies that are available in OpenFOAM, and our main interest is towards the simulation of coupled fluid structure interaction problems. So in today's presentation, rather than concluding about any particular physics, I would try to take you through two particular ongoing research problems in my group that we are tackling using overset meshes. Now, starting with overset mesh is actually one of the special part of the class of dynamic meshing techniques. And why do we need dynamic meshing strategies? Because it allows mesh motion for accommodating moving bodies and or particularly deformation of the bodies in case of fluid structure interaction problems. And apart from overset meshes, of course, you all know that OpenFOAM allows other dynamic meshing strategies such as arbitrary mesh interfaces, allows us to use sliding meshes, as you can see in the first animation. And then we could also use the mesh morphing, which is the traditional Laplacian diffusion of the meshes for the mesh deformation problems. And the third one that is of particular interest of today's presentation is of the overset mesh. So these three animations basically give you the brief overview of how we can tackle the same problem, in this case of flapping airfoil, by using different dynamic meshing techniques. However, each of these has some pros and cons in terms of stability, accuracy, and feasibility of tackling the complexity of the problem. Now, so just to review, what are the overset mesh techniques? In case of overset meshing strategy, as we all know that we have multiple disconnected component meshes. In this case, particularly in this example, if you see that if we want to simulate flow over a cylinder, we could actually take three different disconnected component meshes. One is the Eulerian background mesh, which is all here. One could be the refinement zone around the around the cylinder, and the third one could be the actual structural patch over which we actually impose the boundary conditions. Now, actually, overset mesh, why it is particularly useful for fluid structure interaction problem? Because it actually allows us to simulate a very high deformation or high displacement and a high amplitude of displacement of the moving bodies, which possibly would not be feasible to do successfully using the traditional mesh morphing or remeshing techniques. But as I said, it actually involves multiple component meshes which are disconnected and moves over each other. And how are these component meshes connected to each other in terms of physics? Because the connectivity between these component meshes is obtained through the interpolation techniques in the overlapping areas. And as we all know that because these meshes are disconnected, they can actually theoretically intersect each other, although the physical solution might be not accurate. And as there are numerical interpolation techniques involved in overset meshes, we get numerical diffusion in the solution, and we have to be very careful to validate our results and compare with the traditional mesh deformation cases. Now, one very good tip that we all aware who uses overset mesh, that in overset meshes, the cell size close to overset patches should be similar to minimize the interpolation errors. Now, what is the grammar of the overset mesh looks like? As I said, we have multiple component meshes, so we have to generate these component meshes separately and merge together. Then we have to be carefully define the overset patches where the interpolation takes place, such as here, this nice schematic I've taken from a tutorial of my colleague Joel. You can see that white dotted lines basically shows the overset patches, which is very important to define. And the third very important task here is to define the priorities of the volume of cells or the grid zones, which have to be assigned in terms of 0, 1, or 2, so to decide who are the acceptor cells and who are the donor cells. And then we have to actually kind of involve three different kind of cell zones. One type is the whole, where no calculation is done. The other one is the interpolated cells, where basically the interpolation is done, and the blue parts of all these is basically the calculated portion, where we actually solve the governing equations. Now, interesting part here is that if you see that if we see from the background mesh, which is Eulerian and static, and if we see from the moving mesh, our actually the interpolated cells differs, and depending on the different interpolation techniques, how well they can capture this boundary of the moving bodies, that's also very important for these cases. Now, coming to the interpolation methods, we know that there are a different class of interpolation method with different order of accuracy. However, these three are the most popular one. One is cell volume weight, inverse distance, and the least square. And I will just go through a bit of details into it, but also if we solve this problem parallelly, it is very important to choose the appropriate domain decomposition technique to actually maintain this priority of these cell zones. Now, coming to these two particularly popular interpolation techniques that are often used in overset cases, one is the inverse distance. As you all know that it depends on the concerned point within the cell, and the distance of it in an inverse manner with its neighboring cell centers. And the way we calculate the weights to define any scalar or any variable, let's say phi here, which is the summation of I is the stencils cells from I equal to 1 to n. It goes to the weight wi and the phi I. And this wi are actually proportional to the inverse of the distance of the concerned point to the cell centers of the neighboring stencil cells. On the other hand, the cell volume weight takes actually the weighted volume average of the neighboring stencil cells. And we will see particularly for an example that which one actually gives us more better resolution of the unsteady flow fields that we want to capture. You can see here, this is a flow field around a moving square cylinder. You can see, at least for this case and for the solver setup that I've used, the inverse distance, it gives a discontinuity at the interpolation patch or the overset boundary, which is not expected. Whereas by using the cell volume weight, we could actually by carefully choosing the grid resolution, we could actually remove that kind of non-physical discontinuity. Now, in overset mesh, besides the prescribed motion, we also can use the fluid structure interaction algorithms. So one class of the fluid structure interaction problem that I will discuss mostly today is basically the partitioned approached coupled fluid and solid problem with limited degrees of freedom, particularly the 6 degree of freedom motion you all are aware of, are actually well compatible with the overset mesh, where you can see actually a vortex induced vibration of a circular cylinder problem here. However, the second class of problem of fully flexible bodies with a continuous deformations are also being developed with overset meshes, but it is still there are issues and numerical stability issues with the overset meshes when we go for a fully flexible fluid structure interaction problem. Now, when we actually use this overset meshing technique, the one most very useful technique in this case is the linear driven define a refinement zone around our moving body of concern, and then stick it to the center of mass of the body, and it can actually follow our interested body in a linear translation fashion. So in this way, and I will discuss why we need it, we actually do not need a very fine background mesh. However, we can actually move the refinement region itself within which we actually desire to have a better resolution of our solution. Now, the first problem that I would just take you through briefly, where we are actually using this kind of overset techniques, is the wake-induced dynamics of remotely operated underwater vehicles. So, as you might be aware of these problems, that these are very much useful for environmental monitoring within the water underwater environment. Also, this can be used for surveillance and other purposes. And these underwater vehicles are nothing but it works like a blob body with 6 degree of freedom motion. And the main challenge is to control these bodies in the very turbulent wake, when it particularly comes to the proximity of any underwater structures such as offshore marine risers or any other offshore structures, and then which creates a vertical wake which is subjected to the motion of these ROUVs. And so actually to look at to simplify the problem, we actually took a single phase problem as a top view of the problem. If you see that if these ROVs move in the wake of a vertical cylinder, it actually can actually move drastically in the rotational motion or the translational motion. And the challenge is how we can control these ROVs for the inspection of these offshore structures and keep it stationed at a particular point. And to develop that control algorithm, the first thing that we need to know is that what is the 6 degree of freedom dynamics of these kind of bodies. And to start with, the first approach would be to understand it in 2 dimension, and also when the to understand it in the effect of the wave propagation. And if you can see that by linear wave theory, we can actually predict how the waves will behave at different depth of the water, and then we can actually try to imitate this kind of oscillatory flow behavior through the coded boundary condition in our 2 dimensional problem, and subject the body to it and try to understand how the dynamics changes in the presence of one, the effect of the wave, and this two is the vertical wake structure that is generated behind the cylindrical structure. And this is the way we actually kind of design structured meshes for our problem. And this is basically just to give you an idea that there is a fixed cylindrical structure, and this is one of the snapshot of the simulation. When you see that within this oscillatory wave load, and the wake pattern around the fixed circular cylinders gets also oscillatory, and the shading transverses from one side to another. And due to this oscillatory nature of vertical flow, we get very drastic high amplitude oscillations of our ROV, and through that we try to design the control algorithms that can keep it stationed at a particular point. All right. So this is basically just to show you how we implemented the oscillatory inlet flows, which is particularly incomparable to the linear wave theory. We predicted the amplitude and frequency of this wave motion in an oscillatory direction. In the within the first period, half of the period, it goes in the right direction, then it basically goes to zero, and then it comes back to the opposite direction. And within that, you can see the vorticity contours, that the vortex setting around this cylinder actually also gets transversed, and due to which there is a drastic oscillatory load that acts on these 6 degree of freedom flexible square cylinder. Right. And so basically with that, I won't go into the detail of the final conclusion, as basically we are still working on the coupling a control algorithm with these loads. However, I can show you that depending on the non-dimensional numbers governing this physics, such as Kc number, which is the Carpenter number, very well known, and also the reduced velocity, reduced frequency, Reynolds number, we actually get different dynamical signatures of this body, such as periodic, intermittent, or completely aperiodic with some multiple frequency behavior, through which basically this displacement signal now goes to our controller, and our controller decides how to actually restrict the pitch and plunge motion of this body to keep it stationed within this vertical wake. So that's the next step of the future work. But without going further into that, quickly I will go to the second problem that I want to show, where we are using this overset kind of problem for fluid structure interaction problem, and this is the dynamics of free falling plates and disks. Now you can see in this animation how we can actually use that linear driven motion to actually stick it to a freely falling solid flat plates, which is governed by multiple non-dimensional parameters. However, the Galilei number or the Archimedes number and the non-dimensional moment of inertia is mainly governing the dynamics of it. And and this is very nice feature that you can see that when we subject this kind of freely falling bodies to some sort of turbulence or gust, these bodies can actually traverse to any direction, to any distance, which will be probably unfeasible to do simulation with. So we actually can tackle that problem by bringing into the concept of non-inertial frame of reference. However, we also reduce the complexity of the problem in terms of requirement of the mesh resolution by using this moving refinement zone. And just to give you a brief overview of what kind of dynamics we can expect, as I said, that for a given Reynolds number or the equivalent Reynolds number based on the gravitational velocity, which is the Galilei number, we are actually studying the different dynamical signatures of these three-dimensional free-falling disk, which can be steady free fall, which can be a periodic flutter, or it can be a completely chaotic zigzag motion combining flutter and tumbling. Now, another interesting point is that in this kind of problem, the location or the relative position of the center of mass and the center of buoyancy plays a big role. And for example, here you can see that if we do not displace the center of mass, or is in this case, if d equal to 0, we get a chaotic motion. However, if we displace the center of mass to bring in the stabilizing effect or umbrella kind of stabilizing effect, we get a steady fall behavior. Now, as I said, our main idea or the ongoing work that is being carried out is to understand the effect of gust, effect of horizontal gust, and ultimately going towards effect of turbulence, where actually our free falling body can travel anywhere, and which in the inertial frame of reference would be again non-feasible. So we bring in the concept of simplified concept of non-inertial frame of reference with only 1 degrees of freedom above. Here to explain you the concept that in the earth fixed reference frame, you see this white box which is almost like a wind tunnel in the real space, and the wind tunnel is freely falling. Now in the non-inertial frame of reference, what we are interested about, how the disk or the plate which is within the wind tunnel, how would that behave, right? So when actually this wind tunnel falls and the inside disk or plate falls slowly compared to its terminal velocity, it will actually go up, and slowly as it falls with its terminal velocity, it will remain fixed at a position from the perspective of non-inertial frame of reference. Now that actually allows us to actually study the effect of horizontal gust on that, and to understand what type of wake structures are from in the presence of this gust. And we start with the most simplified version of the discrete gust, which is a horizontal ramp gust based on gust ratio, which is the amplitude of the gust, and gust period, which is tg here. And the acceleration of the gust is a function of these two parameters, which is gust ratio and the period of the gust. And you can see from a non-inertial framework perspective, we could actually truncate the effect of the mean velocity, and we see the relative velocity formulation and the dynamics of the recirculation bubbles very nicely. And this is just to show you what are the kind of effect we can expect for different gust ratio and different gust periods, depending on how fast your gust acceleration is and how much longer your gust is. our vortex structures form in that way depending on the setting frequency of the recirculation bubbles, and we get many more interesting dynamics which I'm not describing here in this short presentation. And this is the same videos just to show you what it looks like in terms of the vortex strengths of the circulations, in terms of the vortex cores in the two tips of the disk. Right. So just to give you some confidence that we did the same simulation of a free falling body in a non-inertial frame and the inertial frame, and translated it back and compared it the terminal velocity from with time, and we see very close match, which gives us confidence that in our formulation there is no mistake. And this is also to show you how it looks like in these two different frameworks. So in the inertial is the left and the non-inertial is in the right of my side. So you can see as the plate moves, in actually falls below with the in the when subjected to the gust, how it actually moves in the non-inertial frame. Okay, so this gives you a better idea of what we are trying to achieve. And now I will end my presentation with this final slide where we can actually show you that our this kind of dynamics by using overset mesh, we could actually study a very large parametric space, and we mostly take these two parameter. One is Galilei number, another is mass ratio, non-dimensional mass ratio, and depending on the value of Galilei number or the mass ratio, we get very complex dynamical signatures of these plates when it is subjected to the gust. And our main motive is to finally understand, when we give a horizontal gust to a free falling body, whether it can actually reduce the terminal velocity of the body. Right. So without further going into the physics, this was my motive, was to show you the usefulness of overset techniques in this kind of FSI problems. And I would want to actually publicize these two recent published papers, which actually takes you further to the modifications of these overset methods for deformable bodies. So this paper is a very nice paper in Open Form Journal, very recently published, and this one is published in Mechanica as the special issue of the last Open Form workshop, which actually very nice papers, very nice initial works to take you forward and give you the details of the challenges of using overset mesh for a fully flexible deforming body. Right. With that, thank you everyone for your attention, and I will be happy to answer if you have any questions.
Thank you for your nice presentation, and time for discussion. Yeah.
Hi, thank you for your presentation. I got two questions for you. The first one is like, I'm wondering how many layers do you set for the overset part along the radial direction, I mean the mesh. Another one is like, how do you decide to move the fringe far away from the narrow region to dig the hole, like the strategy? Thank you.
So the first question, if I understand correctly, you want to understand how many component meshes we need, right?
Yes.
Am I correct?
Yes, exactly. Yeah.
So I would say that that is very specific to the problems that you are handling. So if we want to just solve a flow past a stationary body like a cylinder, we probably would need only 3 component meshes. But depending on the motion of the problem, if you do not want to stick your refinement region to be moved with your body, you might need multiple refinement region depending on the motion boundary of your body. However, as I said, that the technique of linear driven motion is very useful in that, where you can stick to only 3 component meshes or 4 component meshes, where your refinement regime can actually translate with your moving body. Does that answer your question?
Okay. So how about like if you because I know like for the overset mesh we have to dig the hole to do the interpolation, right? In the middle of this overset, we don't have to calculate it because that's the for the red one for your
yes, the whole region.
Yes. So how do you decide like to move this region fringe too far away from the narrow region? Like how many layers do you have to set?
I think in my experience, this is a function of the thickness of your, I mean, the distance from your whole patch to the patch of overset patch. So that distance is very sensitive for this simulation. So we have to do kind of a convergence study with different distance of the overset patch from the whole patch, and we have to see where this kind of fringing effects has minimal effect on it, whether, I mean, my experience is that we cannot make it redundant. We can reduce the effect of this diffusion by choosing the cell size of these component meshes at the uh, overset interpolation zone exactly same. In that case, our error will be minimum, but the distance from the whole patch to the overset patch is a parameter which is subjected to the convergence for your particular problem. That's how
Okay.
I go about it.
Okay, I got it. Thank you.
Thank you.
Thank you, Shannon, for the very nice presentation. I have a question regarding to something you referred during the presentation, because you mentioned, and just before you also mentioned again, that you should keep the same cell size in order to minimize the error. But then you showed a refinement region that is clearly doesn't have the same cell size of the background mesh.
Yes,
are you doing
because
it because far away?
yes,
Because
I understand completely. So yeah, just to answer your question is that I do not care about the flow transition or flow behavior that is happening, or the discontinuity, even if it is happening uh, at the boundary of the background mesh and my refinement region. So I keep the size of my refinement region big enough so that all I care about the accuracy and the resolution of my flow field within the refinement region. But of course, that's a loophole. I completely agree with you. So if you want to make more accurate meshes, I normally use a gradient in your background mesh, where basically you can start with a gradient to have a closer cell size to the refinement region and then make it very big towards the boundary.
Thank you.
Thank you.
So Miguel, just to comment on what you asked about overset region interpolation. So this is an ongoing legend from overset mesh community about pressure fluctuations. And in fact, it's nothing to do with that. As you move the top mesh at the bottom mesh, you will be activating and deactivating some cells. And when people say that the cell volume on the forward mesh and the background mesh needs to be the same, it is because we don't initialize the old value of U in the cell that you have just uncovered. Okay, so there was an obscure paper in one of the ONR conferences about 15 years ago where the guy figured it out. Okay, and it comes from the fact that as you move the mesh from one position to the other, the integral of the DDT term for all time value is different than the integral for the DDT term in the new time value. And that gives you a little blip because the pressure gradient needs to accelerate everything. So all of this stuff is numerical bullshit, and it can be fixed by rescaling the U-old in the cells that have been converted from dead cells into live cells in the donor acceptor recalculation. Okay, this is not well known. I have implemented the fix in foam extend, but for the record, if you people have a problem with that, integrate the kinetic energy before and after the initialization, and you can rescale it for that little factor of the new cells being activated or deactivated. But Shandan, in your results, I didn't see any problems with the pressure fluctuations. Did you have big problems with the pressure?
Not really. I mean, I didn't see such unphysical fluctuations or periodic fluctuations. But I will really look into the implementation in foam extent. Thank you, Professor Jaisak. It's interesting.